Today, we're focusing on environmental impact assessment, specifically how construction materials influence the sustainability of a project. Understanding the full life cycle, from carbon emissions and water usage to waste generation, is crucial. By taking a comprehensive view, we can identify practical ways to reduce these impacts and make smarter, more sustainable building decisions. Material choices are at the heart of this, shaping the overall environmental footprint of every construction project we undertake. Before a building even starts operating, a significant portion of its environmental impact is already locked in. This begins with the extraction and processing of raw materials, which sets the baseline for the overall environmental cost. The very first major source of disruption comes from extracting these materials, which has serious consequences for the land. Natural habitats are disturbed and landscapes altered permanently. Additionally, this extraction and the necessary hauling are energy intensive, relying heavily on fuel. As a result, emissions are generated right from the start, embedding environmental impacts well before any construction assembly begins. Understanding this baseline helps us see how the entire life cycle of a building contributes to its environmental footprint. When we look at life cycle analysis, it's important to understand that environmental impacts don't just happen at one point. They accumulate throughout the entire life of a material, from extraction all the way to its end of life. Starting with extraction, raw material sourcing can cause land disturbance, habitat loss, and depletion of natural resources. Moving on to production, that's where manufacturing demands a lot of energy, generates emissions, uses water, and produces waste. Then there's transportation, which often involves long supply chains, adding fuel consumption, packaging waste, and freight emissions. Finally, at the use and disposal stage, factors like durability, maintenance, reuse, and end-of-life recovery really influence the overall impact. The key takeaway here is that the best way to minimize effects is to take a whole-life perspective. Design teams need to evaluate materials at every stage, not just focus on upfront costs. This comprehensive approach helps us better understand and reduce the full environmental burden. Let's take a closer look at the embodied carbon associated with different building materials. Embodied carbon refers to the total greenhouse gas emissions generated during production, transportation, and installation of a material. Here, aluminum and steel stand out as the materials with the highest carbon intensity. In fact, aluminum emits about 13 times more carbon dioxide equivalent per unit than wood, which is the lowest impact option in this comparison. To put in numbers, aluminum has an embodied carbon of 200 kilograms of CO2 equivalent per unit, followed by steel at 145, then brick at 55, concrete at 35, and finally wood at just 15. This means that choosing materials like wood can significantly reduce the environmental footprint of a construction project, while aluminum and steel contribute much more heavily to carbon emissions. Understanding these differences is crucial for making sustainable decisions in building design and construction. On this slide, we're looking at the operational view of water management in concrete production and related activities. It's crucial to monitor key factors like water withdrawal, the proportion of recycled processed water, runoff quality, and contamination pathways, especially in storage and wash areas. These are essential touch points where water use and contamination risks are most significant. A best practice to follow here is maintaining a closed-loop system. This means reusing processed water as much as possible and isolating polluted flows before they're discharged, minimizing environmental impact. Water use here isn't just about availability. It's also a pollution concern. Activities like concrete production, aggregate washing, and on-site cleaning increase freshwater demand and often carry sediments, alkaline runoff, and chemical residues into nearby ecosystems. To mitigate these impacts, the focus should be on cutting water withdrawals first. Then, efforts should shift to controlling discharges by employing methods such as recirculation, treatment, and effective runoff capture. Water intensity tends to rise quickly during cement mixing, dust suppression, and material washing, so managing usage during these processes is critical. The primary risk we face is runoff contamination. Untreated wash water can raise the pH of surrounding soils and waterways and transport fine particles, causing significant environmental harm. Addressing these risks effectively is key to sustainable water management in these operations. One important insight is that unsegregated waste not only increases landfill costs, but also results in lost material value. Waste in construction is more than just an inconvenience. It's actually a clear signal about how efficiently materials are being used on site. In many urban areas, construction and demolition activities contribute to over 30% of the total solid waste generated, which is a significant portion. Typically, about 10 to 15% of materials are lost due to common issues like over-ordering, offcuts, packaging waste, breakage, and poor storage. However, this challenge also presents an opportunity. By designing projects with sorting, reuse, and recycling in mind, materials like concrete, steel, timber, and gypsum can be effectively recovered and diverted from landfills. This approach not only reduces waste, but also improves overall material efficiency and cost effectiveness. Here, we're exploring three sustainable material options that can significantly reduce environmental impact in construction. First, we have reclaimed wood. This option extends the life of existing materials, avoiding the need to harvest new virgin wood, and helps reduce landfill pressure, making it a great choice for both interior and structural uses. It's all about reusing rather than extracting new resources. Next is recycled steel. Steel with high recycled content helps cut down embodied emissions, while still maintaining the strength, durability, and value that steel provides. This option supports a closed-loop system, meaning the material can continuously be recycled and reused, minimizing waste. Finally, we have low-carbon concrete. This is achieved by using clinker substitutes and optimizing the mix design, which lowers the cement intensity, a major contributor to carbon emissions, without compromising the core performance of the concrete. Together, these lower impact substitutes offer practical and effective ways to make building materials more sustainable, reducing our overall carbon footprint while ensuring quality and durability. Here we focus on our mitigation framework, which outlines key strategies to reduce the life cycle impact of our projects by changing what we specify, how we source, and how we build. First, specifying lower impact materials is crucial. We prioritize recycled steel, supplementary cementitious material concrete, and certified timber. Using environmental product declaration data helps us compare embodied carbon before material approval, ensuring we design based on performance targets rather than outdated assumptions. Next, sourcing and transporting smarter makes a big difference. Favoring regional suppliers cuts freight emissions and reduces delays. We also bundle deliveries and optimize logistics across trades, while screening vendors for their water, waste, and energy management practices to support sustainable supply chains. Reducing waste on site is another priority. We standardize dimensions to prevent excess offcuts or overordering and separate waste streams for reuse, recycling, and material recovery. Importantly, we track waste intensity as a key project performance indicator instead of treating it as an afterthought. Finally, designing for circularity helps us minimize long-term impacts. We specify assemblies that can be disassembled, repaired, or reused, extend service life with adaptable layouts and durable finishes, and plan end-of-life pathways right from early design decisions. Overall, the goal is to build less impact into every specification we make, ensuring sustainability is integrated at every stage of the project. In this case study, we see how net positive performance can be achieved by integrating low-carbon materials, water reuse, and circular design strategies from the very beginning. The project reduced embodied carbon by 42% compared to a conventional baseline by using mass timber, supplementary cementitious materials in concrete, and recycled steel. This shows a significant upfront reduction in environmental impact through thoughtful material choices. Water usage was also dramatically cut by 58%, thanks to captured rainwater and on-site treatment systems that minimize the need for municipal water. For construction waste, an impressive 91% diversion rate was reached by utilizing prefabrication techniques and take-back material contracts, which help keep waste out of landfills and encourage reuse. Interestingly, operational energy saw a slight increase of 12%, but this was more than offset by annual renewable energy generation, exceeding the total building energy use, resulting in a positive overall energy balance. The project itself is an urban mixed-use retrofit, designed with timber and low-clinker concrete, achieving LEED Platinum certification. With a payback period of 8.4 years, it clearly demonstrates how sustainable design can be both environmentally and economically beneficial. Here we explore the compliance landscape defining how projects measure material health, resource efficiency, and environmental performance. Three leading frameworks guide these standards: LEED, BREEAM, and Cradle to Cradle. It's important to understand that thresholds for these certifications vary depending on region, building type, and the version of certification you're pursuing. The key principle here is to specify materials that not only meet your project certification goals, but also align with measurable impact thresholds, ensuring both compliance and meaningful environmental benefits. Starting with LEED, its primary focus is on whole building sustainability and carbon-conscious procurement. The key criteria include environmental product declarations, low-emitting products, recycled content, and transparency in sourcing. Achieving LEED certification involves earning points that range from certified all the way to platinum. BREEAM, on the other hand, emphasizes life cycle impact, responsible sourcing, and construction management. It assesses factors like life cycle assessment performance, certified timber, waste management plans, and pollution controls. Projects are rated from pass to outstanding based on weighted scoring. Lastly, Cradle to Cradle targets material health, circularity, and safer chemistry. It requires ingredient disclosure, promotes reutilization, renewable energy, and water stewardship. Certification levels go from bronze up to platinum, achieved by meeting criteria across various categories. Understanding these frameworks helps ensure your material choices meet rigorous environmental standards while aligning with your project's sustainability goals. Now, let's focus on implementation, which is about turning your sustainability goals into a consistent, repeatable material selection workflow. This slide presents a practical checklist designed specifically for procurement, design, and site teams to ensure these goals are integrated into everyday processes. At the core, the execution lens here highlights 6 essential steps. First, conduct lifecycle material assessments to understand the full environmental impact of your materials. Second, source certified sustainable suppliers to guarantee the materials meet recognized standards. Third, set embodied carbon specifications that set clear boundaries on the carbon footprint allowed in your materials. Next, design for reuse and recovery, which ensures materials can be repurposed or recycled, minimizing waste. Fifth, train your teams on low-impact procurement so everyone involved understands and prioritizes sustainability in purchasing decisions. Finally, track performance continuously and update your standards as you learn and improve, making sure that lower impact materials become the default choice rather than the exception. By embedding impact checks early in the process, we can shift the norm towards sustainability throughout the entire project lifecycle. This checklist isn't just a set of tasks. It's a roadmap to making meaningful, lasting changes in how materials are chosen and used. Looking ahead, the path forward in construction is clear. We need to build with materials that proactively reduce environmental impact before these impacts turn into risks. The future of construction will be shaped by a focus on lower embodied carbon, cleaner supply chains, and circular design strategies implemented right from the start. Assessment moves beyond just ticking boxes for compliance. It becomes a crucial part of the design process that informs smarter choices. By measuring life cycle impacts thoroughly and selecting materials that not only perform well initially, but improve over time, we create a future-ready built environment. The key is to act early, integrating these principles from the very beginning to ensure sustainable, resilient construction that benefits both people and planet.